Hi there, welcome back to another Study With Me session. My name is Amy. I'm the headmaster tutor at Pinnacle Coaching College. So today what I've got for you is the second part on vectors, which will be relevant for our Extension 1 mathematics students in New South Wales or even outside of New South Wales. You might find this helpful. So if you haven't seen the first part, I've linked it down below. But what the first part is just an introduction on vectors and how to do vector addition and subtraction. So all that moving arrowheads to tail, that kind of thing. So if that's something you need to work on first, watch that video first, because this part is all about working in the component form, which is more heavy algebraic manipulation, and obviously there's a lot of rules and formulas I'll introduce in this segment and show you some examples as well. So let's get straight into it. Okay, so in terms of what to expect, so first of all, I'm sort of now moving off just vectors being purely just arrow things you manipulate and talk about, well, how do we represent vectors on the Cartesian plane? And then we'll also look at how to perform calculations in the component form. And we'll also introduce, well, what is a dot product of vectors, which is also known as the scalar product. And we want to look at projections as well. So scalar projections, vector projections, what are they? How do you calculate them? I mean, most of these are just formulas. So it's just about knowing what to do with the formula and then just pretty much it and take it from there. And what I'll also explore in the last part of this lesson is take a sneak peek at some of the exam questions. So you may or may not have seen these questions before, but the NASA, forgot what it stands for, but they've uploaded a sample HSC paper that is for the new syllabus, and there are a couple of vector questions in there. So that's the one I'm going to show you just to see how we tackle it and sort of tying in all the concepts together in that question as well. Let's get into it. All right, so what is a vector? I've kind of talked about in my previous video. It's just little arrow things with a magnitude and direction. The key point for this lesson is about, okay, it can be represented in multiple forms. It can be represented as a pair of coordinates, so for example 2, 3, and literally what it looks like on the diagram, let me draw this. So imagine you're plotting the point 2, 3. Okay, and from the origin you join a line to that point. Let's say OA. Yeah. So vector OA represents the point 2, 3, and in fact OA is what is termed position vector. So what is a position vector? It's literally any arrows, any vectors drawn from the origin, and these arrows are such that they actually point to the point it represents, because as we've learned in the previous lessons, vectors are essentially the same thing if they have the same magnitude, same direction. So in other words, when we're representing this on a diagram, if I draw an arrow roughly pointing in that same direction, yeah, with the same length, yeah, let's say that's the same length, let's say this is 2 by 3 as well, yeah, 2 by 3, then they actually represent the point 2, 3. They both represent the point 2, 3, but that's not going to point to the point 2, 3, right? So that's what our position vector is essentially. Now this can also be represented as a column vector, which kind of looks like that. It's pretty self-explanatory. X coordinate goes here, y coordinate goes here, and component form xi, yj. So the I and j axes, I is sort of like the horizontal axis and j is sort of the vertical axis. That's essentially it. To be honest, from a graphing standpoint, there ain't much difference across all three. And from an algebra manipulation, you want to work in component form. And as you'll see later, well, a lot of the rules around the manipulation is very much like algebra, and that's why we like the component form. And in terms of magnitude and direction, I mean, magnitude is literally about the length, right? So the magnitude of OA in this case would have been, so think Pythagoras, so it's a 2 by 3 triangle, so square root 2 square plus 3 square. Okay, so that's 9 plus 4, root 13. Or more generally, the magnitude in the component form is basically square root x squared plus y squared. That's essentially it. So x squared, y squared is basically Pythagoras. Okay, and direction often we are working with, or as an indication, just look at the angle, and that can help us work out the direction. But that's pretty much it. All right, so just having a look at an example first. Looking at how to manipulate in the component form, and I want you to see through these examples how similar to algebra it is. Like the I components, you treat them as like terms. The J components, you treat them as like terms. So yeah, you add it like you would in algebra. So A plus B will equal to 2I plus 4J minus 5I plus 3J. All right, so 2 minus 5 is negative 3I. 4 plus 3, 7J. Done. All right, let's try the other one, B minus A. All right, expand the bracket. And then minus 7I, and then 3 minus 4 minus 1J. That's it. And then finally, if you have multiple apply to it, so you expand the brackets first, multiply first, and then deal with the, I guess, like term collection. You can think of it that way. Nothing too hard. So 8. Now, if you want, you can pause the video as well, yeah, and try that on your own. You'll learn a lot more that way rather than listening to me baffling on about this. All right, so I'm making sure, yep, that's 5. All right, so that's pretty much it. All right, I hope that makes sense, and that's why the component form is very useful. It works like algebra. Okay, so the next concept I want to talk about is the relative position vector. Now, I just want to draw this up first. Now, while the first part of today's video, it's more or less just working on the algebra components, right? So 3 minus 2. You know what? I'm going to clean that up. Try again. Yeah, this is kind of low, so I want to draw it low. Okay, so 3 minus 2, right? So that's A, and minus 1, 3. Got that. Alright, you know what I mean. Now, we want to calculate the vector joining between these 2 points. So let me just join them up as best as I can. There we go. AB, so pointing towards B. Now, before I dive into, how do you determine a vector like that? I want to sort of take a step back and talk about subtraction vector very briefly. So Now, I always try to explain this to my students because I know once I put like a line joining 2 points on the diagram, like, what is that? How do you calculate that? All right, so going back to the parallelogram rule. So if I have vector A, vector B, and remember the parallelogram rule. God, why is it so ugly? Sorry, I'm struggling to draw a straight line. Ah, there we go, good enough. Okay, so remember, this guy here, I won't draw it in, but this guy pointing in that direction is the addition vector. And the other diagonal is often a subtraction vector. So what you notice, let's say I point it this way. That would be A minus B. Yeah? So notice that this red arrow sits on two arrows that are attached at the tail and both sort of pointing away from the where they meet, right? So this is often sort of the pattern you look for when it comes to subtraction vectors. Yeah, if you have two vectors adjacent to each other pointing away from the tail end, you're looking at a subtraction vector. And how do you determine what that value is wherever the arrow points is the one that goes first. So in this case, it's A minus B. So minus B, if you think about what that means, you flip the arrow. I don't want to mess up the diagram too much and confuse you, but that would have been minus B. So you see how this is basically adding A minus B together? That's the addition vector in that sense. So key point is, when you have a vector joining 2 points, you can think of it as a subtraction vector. You see how this, if I draw the position vector for A, position vector for B, yeah, this is the arrow. This is the arrow, yeah, connecting the two heads. So in this case, AB is equal to, so it's pointing towards B, so it's OB minus OA. All right, so that's sort of the, I mean, you can work it out by thinking vector addition, which way the arrow points, but that's sort of the very quick way to look at a vector and know which way is which, right? So, so I'll minus it as so they are component form, right? So minus I plus 3j, 3I minus 2j. Now you can obviously work in any of the other forms. I just want to keep the algebra simple. And then minus 4I plus 5j. Right, so that's it. Now, if you actually put this on a piece of graph paper and draw it very accurately to scale, you can actually count, like it should be to the left by 4 and then up by 5, because that's what this is saying, yeah? So if you try to count how many left, how many up to form that vector, that's what you're looking for. All right, so that's it in terms of a relative position vector. Let's talk about the dot product. All right, dot product or the scalar product. There are two formulas for this. I'll talk about the first one. So if you have two vectors, A, B, and you know the angle in between, then A dot B is magnitude of A, magnitude of B, cos theta. Okay, I'm not going to derive where this expression came from. I'll say for our purposes, just know that's the result. And this result actually creates a lot of interesting properties, as we'll have a look at very soon. So for example, let's say we've got two vectors, A, B, with an angle of 50 degrees. So that's what this is saying. And the magnitude of A is 3. So this guy is 3. This guy is 5 in length. So using the dot product formula, so 3 times 5 times cos 50. That's pretty much it. A very self-explanatory formula. So you should get 9.64 on that one. Okay, so as I mentioned, does produce a lot of interesting properties. So let's explore them a little bit. So first of all, when you have parallel vectors, now there are two ways that vectors can be parallel to each other. They can be parallel to each other in the same direction. So for example, A, B. Now, key point is if they're both pointing in the same direction, they're not going to make an angle in between the vectors. So in this case, the dot product is going to be just the magnitude of A times the magnitude of B, and it's going to be cos 0, cos 0 is 1, so it's just that. Yeah, magnitude of A times magnitude of B. If they're pointing in the opposite direction, let's say like that, then it will be magnitude of A, B cos pi, or 180 in this instance, and cos 180 is minus 1. So if you, I mean, it sounds a little bit deceiving. It's a scalar product, but you can get a negative value, but that negative value just simply means they're pointing in the opposite direction. That's pretty much all it is. Or basically, as you will see in some of the examples, when your angle between the two vectors are obtuse, that's when you start getting negative values. All right, another one that we'll use very handy, perpendicular vectors. Okay, so that will be 90 degrees. So the dot product will be cos 90 or cos pound 2, and cos pound 2 is 0. Alright, so when you do the dot product of perpendicular vectors, the main thing is they go to 0. And then last but not least, I will say from our perspective, we use this property, the perpendicular vector property, and this next one, equality, the most. In terms of the type of question that comes up and the manipulation required. So if you have A dot A, for example, so obviously they would point in the same direction, being equal vectors. So it will be magnitude of A times magnitude of A times cos 0, which means you get magnitude of A squared. Now this particular result is very, very handy, and you'll see that it comes up a lot in a lot of textbook questions, exam questions, some of the harder ones that require a little bit of thinking. That particular property get used a lot. All right, so let's have a look at an example in component form. So what I'm going to do, so far this is sort of done knowing the length of the vectors and the angle in between the vectors. Now you might not always know that, and you don't want to have to work it out every time. So there is another way to do it, and is to do it in component form. So let's say if I have two vectors, A is x1i plus y1j, and B is x2i plus y2j, the dot product is actually very, very simple in component form. You multiply the x components together, and well, or the I components together, and then the y components, and add them together. That's it. Okay, so in this case, we are doing I plus 3j minus 2i plus 4j. All right, so very simple, x times x, so that's 1 times negative 2, 3 times 4, so 1 times minus 2, 3 times 4, add them together, 10, that's the dot product. All right. So, I'm going to introduce another concept called the unit vector. So, unit vector, so imagine what this looks like. So, it's 2 minus 3. So, I'm just going to draw a tiny one just to help you conceptualize. So, 2 minus 3, so it's down here. All right, so that's what vector C looks like. I've got the C, can't read it. There you go. Okay, what the unit vector is in a nutshell is take that vector and shrink it down so that it only has a length of 1 unit. Okay, because right now it won't have a length of 1 unit. In fact, if you check it, 2 squared plus 3 squared, so it's actually root 13. Okay, so we're trying to shrink this vector down so it's 1 unit in length. That's what a unit vector is. So how do you calculate unit vector? So unit vector, it's sort of the vector with a little hat on top, is you take the vector and just divide it by the magnitude. That's it. Okay, so in part A, so how we calculate that is the vector on magnitude. And that's it. I think I'll leave it not rationalized. All right, so the next we want to find a different vector of 3 units but in the direction of C. So imagine what we have right now. We have unit vector, which is 1 unit pointing in a particular direction. Okay, and we want to create a vector D which basically make this 3 times. Okay, so D is 3 times the unit vector, right? If you want to get it into the same direction. So that's all it really is. It sounded more complicated than it actually is. All right, so that's it. Without rationalizing it, you can rationalize it as well. All right, so what is the unit vector used for? So it's going to be used for in our calculations coming up. So first of all, I want to talk about scalar projections. Okay, so what is a scalar projection? So imagine I have vector A and I have vector B. What I want to do is project A onto B. So what I really wanted to do here is break this up into vectors that will add back to your vector A, and this is the scalar projection. Well, this is the actual projection of A to B, right? It's projected onto the direction of B. Let's call that C. So what a scalar projection is basically the magnitude of that particular vector. That's what we're after here. And how you calculate that is you take the vector A and you take the product with the unit vector of B. So basically take vector A and then just turn it into sort of pointing towards B. That's essentially what's happening here. And I won't go into where this formula comes from because I don't think that's the purpose of our video today. I'm sure you can read up on it in the textbook in any case, but that's the formula we'll be working with. Having a look at this one, if we want to project A onto B, so A onto B, yeah, and we're looking for scalar projections. So 2i minus 3j and 4i minus 5j. Now remember what the unit vector is. So unit vector is vector b over the magnitude of b. So that's what I'm doing here. So vector b over magnitude of b. Okay, and then doing the product on top. So it's 2 times 4 minus 3 times minus 5. And then on the bottom, just add that together. So that's root 41. Yikes, that looks terrible. Okay, and then just add that together. That's 23 on root 41. Now, the fact that this is positive actually tells me a couple of things. It tells me that vector A and B are probably like this. It's going to have an acute angle. Usually, if you have an obtuse angle, as I mentioned before, you're going to end up with a negative scalar projection. Yeah, because the negative just suggests the angle is obtuse, essentially. Okie dokie. So we've done the scalar projection. Now let's talk about vector projection. So remember, the difference between scalar and vector is this. Scalar is magnitude only. Vector is magnitude plus direction. So basically, it's the same diagram. So let's say our vector A, vector B, and I want to project it in the direction of vector B. So we are looking at these two vectors. Okay, it's supposed to be perpendicular. Didn't draw it too well. All right, so vector C is basically the vector projection of A onto B. The only difference compared to scalar projection, remember scalar projection only gets you the magnitude, right? So now we need a magnitude and direction. So magnitude and direction by multiplying the unit vector, right? Unit vector gives you the direction component without the magnitude because magnitude is 1. So that's all it is. So the magnitude of C, if you come back to this, it's basically calculated like that. So that's the formula I'm going to steal. Okay, that's it. And if you're after the vector projection that's perpendicular, so basically this guy here, it's just A minus C. Yeah, you see how these are, how will I explain this? So these are like two arrowheads, and remember I talked about a while back, the line joining two arrowheads is a subtraction vector, and wherever it's pointing, it's the vector that goes first. So in this case, it will be A minus C because it's pointing towards A. All right, so it will just be A minus that thing. All right, so that's essentially it. I believe most of these formulas are sitting in the reference sheet. You don't need to remember them, but obviously I say this to my students every year, don't be over-reliant on the reference sheet. You're not going to have time to slowly flick through and look for the perfect formula. The more you remember, the faster you're able to answer any exam questions. And also it's also a bit of a chicken and egg type of situation, right? Knowing what tools you have to work with gives you a better ability to solve the problem. If you have to flick through the sheet and try to decide which one is relevant, well, other people are like miles ahead of you and you're still deciding which one to use. And obviously your thought process will be very different, yeah, compared to someone who already know all the formulas. So that's kind of my suggestions around the formulas. Remember as many as you can. If you are not going to remember it, then make sure you know where it is on the reference sheet so you know, okay, I need that formula, and you just like flick to the page and that's the one you use. All right, so let's have a look at an example. So the vector projection. All right, so first of all, vector projection, I'll just write the formula again. All right, so that's how we're going to calculate. So vector A dot vector B over the magnitude. Magnitude of that will be 4 squared plus 5 squared. Okay, and then all of that times the unit vector again. Okay, so calculating that. I think we may have done this one already. Let's see. 2 minus 3, 4 minus 5. Yeah, we've done this one already. Okay, so it was 23 on root 41. So I'm just going to steal it. So this part is 23 on root 41. Yeah, because we've done it already, the scalar projection. And then this guy here is 4i minus 5j. And that would be root 41 also. Okay, so that's 23 on 41. So you can see, unlike the previous question, it was just a number because it's scalar projection. This time, it's a vector form, right? It's actually got a direction attached to it. And part B, very simple. It will just be A minus this. Okay, and then just a matter of making it one fraction. 41A on 41. I think my I's and J's are getting a little bit mixed up now. Let's see. All right, and then you just clean that up. So that should be minus 10i minus 8j. And I'm just going to factorize it. Now, a very quick cross check. So going back to what a vector projection is, that's what you've calculated, these two vectors. So these two add back to give you this vector. That's the addition vector. Okay, so that's your cross check. Right, if you add these two together, you can quickly add the numbers. So 23 times 4 minus 10 should get you back to 2. Yeah, so that's how you very, very quickly check, oh, did I do this right? Because there's a mess of numbers. Yeah, that's pretty much it in a nutshell. Very simple. It's following the formula and then applying cross-check where appropriate. All right, so majority of the video so far is just about here are the formulas, let's see how it's applied. So more importantly is, okay, how do I handle a problem like this? So these are the type of problems that's more likely to come up in an exam. So in this question, we've got the points. P and Q represent the position vector C plus D. So I'm just going to write it in, C plus D. And 3c minus 2d. So this one here is 3c minus 2d. And we want to find PR. Let's draw this thing. Okay, you want to find that. Now, first of all, I just want to observe that to calculate PR, you kind of need to know what OR is, or that would be one of the easier ways to do that. Because I don't know if you can see, this is sort of the vector joining, yeah, two arrows. So if I make this arrow this way, yeah, joining two arrows, that's in my mind subtraction vector, right? Subtraction vector. So in other words, PR is equal to OR minus OP. Yeah, because it's pointing towards R. So OR minus OP. Okay, so with that in mind, I'm actually going to find OR first. Now, OR is interesting because I don't know if you notice this is a parallelogram. What happens in a parallelogram? That's actually the addition vector. yeah? Or in other words, OQ is actually OP plus OR. Does that make sense? That's the addition vector, okay? And we know what these guys are, so I'm just going to write them in. So that's how we're going to work out what OR is. So 3 minus 1, so that's 2, and then minus 3. Okay, so let me see if I can squeeze it in here. There we go. Okay, so that's what this guy represents. So coming back to this guy here, PR is the subtraction vector, so OR, which is 2C minus 3D, minus OP, OP is C plus D. So that's C minus 4D. All right, so that's it. So I'm just going to write it here, C minus 4D. Okay, so that's how we worked out PR just by manipulating the other factors. Now, suppose that it is a square. Use the dot product to prove that thing. Okay, so what I'm going to do, I'm just going to copy this thing. Okay, so just so that we have it in front of us. All right, so we are trying to prove, let me just write the question out for you. And the hint was, well, we have two things. The hint was, well, this is a square, OP QR is square. And we were supposed to use dot product. Okay, so the thing with a square, I mean, just sort of redrawing this a little bit. Because what we have in this question are the vectors that are adjacent, yeah, to the origin as well as the diagonal. So that's probably where I will think, okay? So first of all, naturally, all four corners of a square are actually 90 degrees. That means they're perpendicular. Remember, perpendicular vectors have a dot product of 0. That's what we're going to use. So the dot product, okay? So OP and OR should have a dot product of 0, okay? And that would be C plus D dot 2C minus 3D equals 0. All right, so then expanding this, so I'm just going to do this manually, so C times that, and then that times that. Now also remember that the property, so I'm just going to note it on this side. So the property, if you have the product of equal factors, you get the magnitude square. So that's going to help us simplify these two terms a little bit more. And I'm just going to simplify these guys. Now what you will notice in terms of the results we're getting so far is that we've got two modulus of, not modulus, sorry, magnitude of c squared and 3 magnitude of d squared. But we have an extra thing, right? We have a dot product here. So what I'm going to do, I'm just going to make that the subject. because I don't know what to do with that yet. We'll just park it. Okay, I just made it the subject and park it. But what that means is that we need to figure out what this is. Okay, so just thinking how exam questions, so this is a very typical exam style question. They get you to do a prior part for a reason, right? Why did I look for PR? It's a little bit strange if it doesn't get used in the second part. So that's where I'll look, right? So what do I know about the diagonals of a square? Well, diagonals of a square works like the diagonals of a rhombus, or it's like rhombus, rectangle had a baby, right? So they're equal in length and they're perpendicular. Oh, perpendicular, I can use this property again. So with that in mind, what I'm going to do, I'm just going to again translate this into the next page. So we've got it all in front of us. All right. So the other thing is OPR, sorry, should be perpendicular to OQ. Yeah, the diagonals of a square are perpendicular. Okay, so in other words, that dot product should equal to 0, and they represent that. Again, just expanding it out. Okay. All right, so let me just triple check that it's expanded out correctly. Okay, cool. All right, so again, using the equality of vectors property, so it becomes the magnitude square, so that's minus 14. And that's 8. Okay, so that's good. We've now have two expressions. Again, we've got a c dot d in there. So I'm going to call that 1, and I'm going to substitute that into this guy here. Yeah, I'm going to replace this thing. All right, so 3, don't worry, I'll highlight it for you. What was it? 2c and minus 3d. All right, so hopefully I'm going to manipulate this until we get to the property we're trying to prove. This is taking a lot of room, I have to say. It's like more than induction. Okay, so I'm just copying it here. All right, that's good. Okay, so expand this thing. Quickly put that through the calculator. I don't want to give you the wrong number, 42. All right, so 3 minus 28 is minus 25. 42 plus 8 is 50. Well, that's good. So in other words, if you move that to the other side, and divide both sides by 25, that's it. All that wasn't too hard. But you can see that the recurring properties that came up was to do with the perpendicular vectors. So just to summarize, yeah, there's a lot going on here. So the first step was to work out all the different vectors. So I'm just using the way the questions are prompting me, and that's how most exam questions they actually operate. They try to prompt you, leave you breadcrumbs, yeah, to the correct answer. You just try to follow them, right, and see if you can get to the answer. So first of all, we only knew what OP and OQ, and to find PR we should find out OR. So that's what I've done over here, which is sort of the well, playing with the addition vector, because that's the addition vector of these two things. And then PR is the subtraction vector. Now you don't have to think about it in the same way, because there's so many ways to think about a parallelogram. This is what works for me, and I think that's what works for most students. But if you have your own creative way of understanding vectors and it gets you to the right answer or the same answer, no problems with that at all. So that's the first step. Then the second step is to try to prove this property knowing that it's a square, and the hint was to use dot product. So first dot product I used was, all right, squares, corners are all 90 degrees, so they're perpendicular, so a dot product of 0, and then that expanded into that property. And same with the diagonals. So the diagonals are also perpendicular, so the dot product should go to 0. That gets you a second expression. So I subbed that expression into the second expression, simplified, and then you'll get to the property. All right, so I promised you an exam question. So that was not an exam question, but it's modeled like one. The next one, it's an actual exam question. I mean, if your teacher is feeling extra lazy, which tend to happen with first year implementation, they may have chucked this question in your assessment. So now you get a chance to take a peek at it before it comes up in your exam. This is a sample question that's been written by Nessa as an example of what the HSC question looks like in this area as under the new syllabus. So what we've got here is we've got points P and A on the number plane. The vector PA represent the column vector 3, 1. B is chosen so that triangle PAB is 10 square units. This is 4/5. Find all possible values of PB. Okay, so I need to help you visualize this first. So I'm just going to roughly draw what 3, 1 will look like. Now 3, 1, if I was to plot it, right, it just literally means 3 across 1 high. Yeah, that's what we're looking at. So I'll delete that. Just trying to not mess it up too much. Right, so that's my PA. Now B is some point. I'm just going to pick a random point. Let's say B is here. B is a point so that now it's important to note the information they're giving you, because that affects how you're going to work with the information. So first we know that this is the area is 10 and the length of that is 4/5. Now, just think trigonometry. When you're given an area, there's only so many things you can do to it. Yeah? And I'm immediately thinking, okay, area formula is half AB sine C. Remember that one? That's immediately what I'll be thinking. So, I should probably work out that angle. And do I know the length of this? Yeah, actually I do, because I know what it represents. So if you calculate that, that's √10. Okay, so that's where I'm going to start with. Okay, I don't know the angle, but I know the two adjacent sides. I know the area. So 10 is equal to half AB sine theta. And theta is the unknown in this one. All right, so just cleaning that up a little bit. Let's see. 50. I might try to just squeeze in here so I don't lose you. And then divide the 10 across. Actually, divide the 10 root 2 across. Even better. Alright, so sine theta is 1 on root 2. So theta is equal to, now, the angles is either acute or obtuse, so I don't need to quite pass that in my opinion. So ASTC, so we're looking for the first and the second quadrant answer, 1 on root 2 pi on 4. So pi on 4, 3 pi on 4. All right, I think this question is a bit trappy because I think most students will just put pi on 4 and then miss 2 answers if you leave out 3 pi on 4. Okay, so in other words, B can be like this, or let me do it in yellow. It can be like this, yeah, where it's an obtuse angle, yeah, 3 pi on 4 versus pi on 4. So that's another possible position for B. And as we'll find out soon, there is actually 4 answers because it can happen in the same way on the other side. So it can be like that and like that. Okay, so I don't want to confuse you too much. I just want to give you a situation. You can see the facts you're working with, and then we'll try to work with those facts. All right, so far what we've got is this. So let's go on to the next page. All right, so we've got PA. This is root 10 in length. B. This is 4 root 5 in length, and we've got 2 angle values, pi on 4, 3 pi on 4. Okay, so what do we do with that next? Well, what we're trying to find is PB, okay? So what this vector represents. So what I'm going to do to make things a tad easier for you is I'm going to define PB as xi plus yj. And that's a very powerful technique. If you're finding an unknown vector, just let it be something generic so you can work with it, right? Okay, so first of all, we can do dot product here, yeah? PA dot PB is, now I'm going to use 2 versions of the dot product formula. Well, one of them is because of the way we've got the facts, right? With the magnitude and the angle, that immediately draws me to that formula where you take the magnitude of PA, magnitude of PB, and then cos theta, okay? In this case, it will be root 10 times 4 root 5 cos pi on 4 or 3 pi on 4. So I'll do the 3 pi on 4 later. Okay, so what is that? Okay, 4, 5, 20. 1 on root 2. So that will be 20. Okay, so that's for theta is pi on 4. Theta is 3 pi on 4. Then the dot product will be basically 20 root 2 cos 3 pi on 4, which is negative. Minus 20. Okay, so that's the only difference. All right, so we've got the dot product 20 minus 20 depending on the angle. Then what do we do? Okay, well, what's another way of doing the dot product? Another way of doing the dot product is in the component form. So PA was 3, 1, which is 3i plus j. Okay, PB is xi plus yj. Okay, so another way of doing the dot product is to do it in the component form, which is also super simple. So x times 3, 1 times y, that's it, that's the dot product. Okay, so in other words, 3x plus y is equals to plus or minus 20. Now, what this suggests to me, actually I'll make y the subject, 3x plus minus 20. Okay, what this suggests to me is this. I've got an expression for x and y, meaning I'm probably building a pair of simultaneous equations, and I need something else that link x and y together. So let's backtrack a little bit. How else do we link this together? Well, we know the magnitude, right? That's usually where it's hidden. If you know the magnitude, you can actually link x and y together as well. So magnitude is 4 root 5, and magnitude is x squared plus y squared under a square root. So x squared plus y squared equals to 80. Okay, so equation 1, equation 2. Now we've got our pair of simultaneous equations. Okay, so what we're going to do, now I am guessing that simultaneous equation is not going to be a problem for you if you're doing at least extension 1. So I'm just going to speed through this and just going to write down some of the critical steps. So we've got minus 3x plus 20. So we're going to do them one pair at a time. And 2 is x squared plus y squared equals to 80. Okay, so substituting. Now feel free to pause the video and just try that on your own. Now I'm just going to get straight into the answer. So if you expand this and simplify it, that should get you down to x squared minus 12x plus 32, which factorize. So x is 8 or 4, and then you just sub it back into that one. So if it's 8, you put that back in. That should be -4 or 8. Okay, so that's one set of numbers. So therefore, PB is equal to 8 minus 4. That's one answer. 4, 8. That's another answer. And then you just repeat the same thing for the negative version. So y is minus 3x minus 20 this time. Second equation is exactly the same. And then you sub 1 into 2. So get and then the only difference I think is the sign of the middle term. And then factorize. That means minus 8 minus 4. Y is equal to, so sub that. I'll actually shuffle that up a little bit. Okay, so sub that into there to get the y value. So it should be 4m minus 8. Okay, so I'm just high level crossing in my head. Yep, that's good. All right, so the other answers are minus 8, 4, minus 4, minus 8. And that's it. So it wasn't too hard, but I think with these type of questions, because there is so little guidance, that's why it's just worth 4 marks on its own. If it was more stepped out, it's like, oh, do this, look at this, do that. It wouldn't be as hard. If you think about it, it's just algebra, right? And the hardest part is trying to identify, well, what am I working with? So to summarize for you, right, let's come back and understand what we're looking for. So to start with, we knew the key information that I knew to sort of like go down the path of looking at this formula here, the dot product with the angle in between, is because you're given area. There's very limited ways you can use an area information, half a b sine c being one of them. So that's sort of the direction I headed. I was like, okay, it's something to do with area. Let's figure out what that is for. And we figure out the angle. Okay, we found the angle. So what is angle used for? To find the dot product. And so that's kind of this part, right? So this is for finding the dot product. Okay, so we found the dot product and realized, oh, the dot product is 20 or minus 20. Then, well, how does that help us? Well, let's define PB as an unknown. We can also reframe the dot product as in component form, and then we get a different expression that we can work with, right? So we get an expression for y, and another expression between x and y is to do with the magnitude. So we got a second expression. So once you get these two expressions, just really downhill from there. Very, very easy. Simultaneous equations, pump out all the numbers, you get 4 different potential points. And that is it. So hopefully if this comes up in your assessment, you will completely ace this because now you know the answer. Alright, so this pretty much concludes this 2-part module on vectors. If you haven't seen the first video, I have linked it down below. So that's about vector additions, or what are vectors, vector addition, subtraction, basic manipulation. This video is about working in the component form, so the more advanced questions, and obviously using those original introductory concepts as well. And that should be sufficient to cover you for your next assessment if you're getting assessed on vectors. Now, if you do extension 2, next week I'll create another video that deals with vector problems in complex numbers, because I know that's an area that a lot of students still struggle with. Okay, so I'll continue sort of this streak on vectors, and we'll talk about how it applies in extension 2 as well. But in the meantime, if you have any questions, suggestions, just leave comment down below, or you can reach us by Facebook, email, website. And just a note on our website, we have a bunch of resources that can help you as well. Go check it out yourself. There are plenty of videos just covering specific topics. You might find it helpful just to sort of beef up your knowledge before going into your assessment. All right, well, best of luck. If there are any problems at all, let me know. Bye for now.